Hi, my name's Paul and I'm a Principal Solutions Architect covering container technologies here at AWS. And today I'm going to be talking to you about how you can use Amazon EKS to scale your workloads to 100,000 CPUs and beyond. Last year I started working with a customer who came to me with a really interesting set of requirements. They were looking to move one of their large batch processing workloads from their on-premises environments into Amazon EKS. They were looking to run over 30,000 pods, with each pod having between 2 and 4 CPUs and 7 and 15 gigabytes of memory. So some quick maths shows that this is a pretty large-scale workload, and the customer wanted some help getting this up and running quickly. Now, in addition, they also wanted all 30,000 pods to be running in the same cluster, and in the fullness of time, they were expecting to run multiple permutations of the same job using one EKS cluster per run. Now, this seems deceptively easy. It should be a case of increasing the number of pods to 10,000, then 20,000, then 30,000, and the cluster should take care of everything for me. Cluster autoscaler should take care of scaling out my nodes, and horizontal pod autoscaler and replica set should take care of scaling out my pods. However, it's not always as simple as that. Things don't behave as you always expect when you start to push outside of normal scale. You may find that you start to run out of IP addresses as you deploy a large number of pods into your VPC. You may start to drop packets as you become increasingly exposed to the law of averages at large scale. You may start to hit AWS API limits that you've never even heard about before. You may start to experience issues with core service functionality such as DNS. And you may simply overwhelm the control plane and find that things start to break or behave in unpredictable ways. So the first experiment that I performed with a customer was to scale to 10,000 pods. This seemed like a sufficiently high number that we would probably start to break things, but it didn't seem overly ambitious for our first try. And we were right when we thought that we'd start to break things. We started off by deploying a test EKS cluster into one of the customer's regular VPCs. And because we were deploying hundreds of nodes and thousands of pods, we started to run out of IP addresses after a while. Now, this is a pretty common problem, especially for large enterprises who are looking to integrate their AWS VPCs with their on-premise networks. They often don't have a large number of large routable IP blocks that they can delegate into AWS, and so their VPC CIDR blocks will be necessarily smaller than they otherwise would want them to be. For those of you that may not be familiar with how EKS uses VPC IP addresses for your pods, here's a quick overview of worker node networking. When an EC2 instance boots, it gets an Elastic Network Interface, or an ENI, and that ENI has a primary IP address from your VPC subnet. Each ENI is capable of supporting multiple secondary IP addresses as well, and every EC2 instance type is able to support at least one additional ENI, each with its own primary and secondary IP addresses. Now, different instance types can support a different number of ENIs and IP addresses per ENI. And so you can increase or decrease the number of IP addresses and therefore pods on your worker node by changing your instance type. Now, EKS makes use of these secondary IP addresses by assigning an IP address to your pod, making it routable on your VPC and elevating it to be a first-class citizen of your VPC. You can calculate the maximum number of pods that any given instance type can support by plugging the relevant numbers into the formula shown on screen. And if we look at a specific example, the M5 4x large can support up to 8 ENIs with 30 IP addresses per ENI, and this allows for a total of 234 pods per worker node. Now, the Amazon VPC CNI plugin has configuration parameters that you can use to tune the behavior of the CNI, and this can help optimize the number of IP addresses that are assigned to our worker nodes. Now, I'm going to talk about a couple of parameters here, and for each of these I'm going to make some assumptions, including that the first IP address of every ENI is reserved for the worker node, and that we're running a couple of daemon sets in the cluster, so every worker node will have 2 pods running before we start to schedule any customer workloads. And when I start talking about the number of IPs consumed by a worker node, again, I'm talking about before any customer workloads are deployed. If you want to read about all of the CNI configuration variables that are available for the Amazon VPC CNI plugin, you can do so at the link that I've just put on the screen here. Now, the default behavior of the CNI is to set the warm ENI target to a value of 1, which tells the CNI to warm up one ENI and all available IP addresses on that ENI. As soon as an IP address is consumed by a pod, the CNI will warm up an additional ENI and all the IP addresses available there. Now, we use this as the default behavior because it provides a good balance between IP address consumption and the ability to scale pods quickly. And in our M5 4x large example, this means that the CNI will pre-warm 2 ENIs with 30 IP addresses each, for a total of 60 IP addresses. The warm IP target variable specifies the number of free IP addresses that the CNI will keep available for assignment to pod on the node. The IP addresses, or as IP addresses are consumed by the CNI, the CNI will then add more IP addresses to the warm pool. And it will take these from existing ENIs if there are spare IP addresses, and if there aren't any IP addresses available, it will allocate an additional ENI and then use IP addresses from there. This variable is useful for dynamically scaled environments as it allows you to ensure enough IP addresses are available to quickly scale pods by deploying them onto your worker nodes quickly without consuming an excessive number of IP addresses. So if, for example, you set this variable to 10, then each M5 4x large instance in our example will consume 13 IP addresses across one ENI. Now, this is obviously considerably lower than our default configuration of the CNI where we're consuming 60 IP addresses. Why is any of this important? Well, an M5 4x large instance has 16 CPU cores, and our pods are only using 2 to 4 CPU cores each. So we're never going to run more than 8 pods on one of these M5 4x large instances. And yet, with the default CNI configuration, we're consuming 60 IP addresses per worker node before we've even started to run workload applications. So this is obviously wasteful, but it also means that our VPCs and subnets will need to be larger than they otherwise would need to be. And it means we'll also artificially limit the total number of pods that we can deploy into our cluster. Let's have a look at some of the ways we can help avoid IP address exhaustion in our VPC. So when running at scale, we recommend one EKS cluster per VPC, so that Kubernetes is the only consumer of IP addresses within the VPC. Any services that consume IP addresses outside of Kubernetes will ultimately limit the number of pods that you can deploy into your cluster. For very large scale applications, you're going to need to run a large number of pods, and that means you're going to need a lot of IP addresses. Now, VPCs can support CIDR block ranges of up to /16, which provides over 65,000 IP addresses. With the right subnet configuration using large subnets, you can make over 64,000 of these available to your pods running in private subnets. And this leaves a few hundred left over for things like load balancers in your public subnets. And by tuning your CNI configuration, you can control the size of the warm pool running on the warm pool of IP addresses that's available on each worker node. And this can help prevent IP address exhaustion by stopping the CNI allocating IP addresses to worker nodes that are simply never going to be consumed. Now, as well as designing the VPC to avoid IP address exhaustion, there are some other considerations you should bear in mind when deploying your EKS cluster. For very large workloads, we recommend running one EKS cluster per AWS account. Now, it's common for customers to run controllers and additional services, such as the AWS Load Balancer Controller or external DNS in their clusters. And these services often reach out to AWS APIs and provision and configure AWS resources on your behalf. But for very large-scale workloads with high levels of churn, these services and controllers can sometimes hit AWS API limits and be throttled. For some services, such as Route 53, which is a global service, these API limits are implemented at the AWS account level. And so when you hit these limits, that could also potentially impact any other workloads running in that account. Now, before you deploy any of your pods, you need to consider the type of instances that you want to run your pods on. AWS has a wide range of instances available, including general purpose, CPU optimized and memory optimized families with Intel CPUs. We also have AMD CPUs and Graviton ARM CPUs. And we have network optimized instances which offer high network throughput of up to 100 gigabits per second. Now, the Kubernetes cluster autoscaler expects homogeneous pools of resources in its node pools, but you can mix and match instance types that have the same amount of CPU and memory. So, for example, the M4 4x large and M5 4x large can be used in the same node pool. You can also create multiple heterogeneous pools of resource to make use of instances of different sizes. So you could have a pool for 16 CPUs and 64 gigs of memory, and another pool for 32 CPUs and 128 gigs of memory. You also need to consider the pricing models that you want to use to help optimize the cost of your workload. So EKS supports on-demand, savings plans, reserved instances, and spot instances. Savings plans and reserved instances can be used to reduce the cost of your workload by committing to certain levels of usage over time. And spot instances can help you achieve even deeper levels of discount, but you do need to ensure that your workload can be disrupted and can gracefully shut down within the 2-minute notice period. The key to using spot instances, particularly at large scale, is to diversify. Use as many homogeneous instance types as possible within each of your node pools, and create multiple heterogeneous node pools to diversify further. If you want to learn more about using Kubernetes with spot instances, check out session CMP 402 by my colleague Isaac, where he'll be talking to you about how you can scale Kubernetes for less using Amazon EC2 spot instances. So now we've sorted our EKS deployment so that we're not going to hit any IP address limits or AWS API limits. And we've chosen the correct blend of instance types and pricing models to optimize the cost of our workload. So I went back to the customer and we tried scaling to 10,000 pods again. And this time we were successful. So we pushed on to the next milestone to 20,000 pods. And this time we hoped maybe it would just work. Unfortunately, that wasn't the case. We found some new issues, and I'm going to dive deep into that now. In order to understand what's happening in your application pods, which are spread out across your cluster, you need some sort of agent that forwards logs to a centralized repository for easy searching and analysis. fluentd is a popular open source data collector which runs as a daemon set on your worker nodes, and based on rules that you define, forwards logs to a destination of your choice, such as CloudWatch logs. fluentd will tail the Kubernetes container log files, and it can determine attributes such as the container name, the namespace name, the pod name, and the pod ID from those log files. Now, as we scaled past 10,000 pods, we started to find our cluster was not behaving as reliably as expected. Kube control calls were starting to take longer than normal to respond, and the state of the cluster was not updating as reliably or as quickly as we would expect. fluentd also supports a wide range of community plugins, such as the Kubernetes metadata plugin. This allows fluentd to enrich the container log files with additional metadata from the Kubernetes API, shown here in orange. However, when running at scale, this introduces a problem. On every single worker node, fluentd runs a kubecontrol get pods command across all namespaces and in watch mode to receive ongoing changes and updates to all pods that are running in the cluster. As you scale to hundreds or thousands of nodes, this puts a very large strain on the control plane, which has to request data from etcd and return it via the API to each worker node. So what can we do about this? Well, we can override the default configuration with some custom config that reduces the load on the control plane. We can tell fluentd to skip all label fields from the metadata. We can tell it to skip the container metadata, fields like the container image and the container image ID. We can tell it to skip the Kubernetes API URL and to skip the namespace metadata fields. This particular setting allows the plugin to run faster with lower CPU consumption because it allows the subsequent fetch namespace metadata function to be skipped, which also avoids a subsequent call to the Kubernetes API. We can also increase the number of objects that fluentd caches up here from the default of 1000. Now, why are we doing all of this? Well, ultimately, we want to reduce the number of API calls as much as possible, or eliminate them altogether if we don't need the additional metadata that's coming out of the Kubernetes API. This will reduce the load on the control plane and allow it to focus on doing what it does best, running our cluster. So once we've tuned our fluentd configuration, what does our log output look like? Well, as you can see, it's much shorter than it was before. And now the Kubernetes section only contains information that was already available on the worker node in those container log files. If you need to have some specific Kubernetes metadata fields in here, you can add filters to selectively include them, but this will obviously start to increase the load on the control plane again. So of course, it may not be possible to tune fluentd in a way that provides the information that you want without putting too much pressure on the control plane. And if that's the case, you may need to consider switching to fluentd instead. The two products perform similar functions, but fluentd was designed and built for high performance, and it comes with a very small resource footprint. The main trade-off between the two is that fluentd has a much smaller ecosystem, so not all of your fluentd plugins will have a fluentd equivalent. Fortunately, there is a Kubernetes metadata plugin for fluentd. Now, a common pattern for fluentd is to send logs into a Kinesis firehose, which then sends them onto an S3 bucket, where you can then access your logs and run analytics against them using your normal tools. In the second half of 2020, we launched a fluentd plugin which allows fluentd to output the logs directly to an S3 bucket, negating the need for that Kinesis firehose. And we're currently working on a feature due out in Q1 of 2021, which will allow fluentd to query the pod's API endpoint from the kubelet running on the local worker node, completely eliminating the need for control plane queries for the additional metadata. Once this feature ships, we'll be able to have the best of both worlds, all of the additional metadata with none of the control plane load. Okay, so now we've fixed our issues with our IP limits, our API limits, and our logging daemon, and we've successfully hit our first two milestones. So now it's time to go for gold and scale to 30,000 pods, or about 120,000 CPUs. Now, we were actually able to scale to 30,000 pods without any other major issues, which the customer was obviously delighted with. However, before I come to a close today, I wanted to share some additional insights with you that I've learned from working with other customers at scale on interactive workloads such as websites and back-end APIs that also run on Kubernetes. So when running interactive or non-batch workloads, you typically schedule your pods and use a selector to configure them as part of a service. For each service, Kubernetes creates and maintains an endpoints object in the API, which contains a list of all the endpoints that make up the service. When traffic is sent to a cluster IP, kubeproxy uses this list to send traffic to the actual pods that form the service. And as you scale up your service by adding more pods, the list of IP addresses grows in proportion with the number of pods. Now, why am I telling you this? Well, the Endpoint API was designed in the early days of Kubernetes, when scalability and its implications weren't a major concern. And so they went with the simplest design, which is simply to include all the endpoints for a service in a single object. But now, when we run large-scale clusters with many tens or hundreds of thousands of pods, this can cause problems. And this is because the size of the endpoints object is proportional to the number of pods in the service, because each new pod adds an IP address into the endpoints object. And as the number of pods in the service approaches 5,000, the size of the endpoints object approaches 1.5 megabytes. And this just so happens to be the default maximum size for an object in etcd. And above this size, etcd latency can increase, or the object may even be rejected. Now, according to some research performed by the Kubernetes Scalability SIG, there is a threshold of around 250 endpoints per service, beyond which you will start to experience a degradation in performance within the cluster. Now, this isn't a cliff that you fall off when you scale to 251 pods, but it becomes increasingly noticeable the further past this figure you go. Endpointslices is a new feature that's currently in beta, which will ultimately replace the Endpoints API. The idea with Endpointslices is to have up to 100 endpoints in a slice, which can update independently from other slices. This is obviously a major change functionally, and so it's being rolled out cautiously and in phases, and it will be made generally available in a future version of Kubernetes. So until then, if you are running more than 250 pods in any of your services running on Kubernetes, you should first ensure that you have appropriate throttling controls and caching in front of your services to ensure that you're not sending unnecessary requests to your backend pods and causing your cluster to scale unnecessarily. Second, you should investigate whether you can add more CPU and memory resources to your pods so that they can handle more requests. And third, you should look into whether you can decompose your microservices into smaller, more niche services that perform one single function optimally. Now, when it comes to running at very large scale, the way you test your applications can play a big part in how successful you are when scaling up. We speak to many customers who scale in the following way. They run a certain number of pods for each of their microservices, which allows them to respond to a particular number of requests. When they want to scale their application to be able to respond to 10 times as many requests, they simply scale up the number of pods by 10. However, this has an impact on a very particular object in the cluster, the endpoint object, which can cause a significant increase in the load on the control plane. And so this approach often won't work, or at least it won't work in the way that customers expect. So what can we do instead? So instead of jumping straight into scaling up the number of pods running in your cluster, you should spend some time figuring out the optimum configuration for your pods individually. By varying the amount of CPU and memory assigned to your pods and measuring the number of requests that a small number of pods can support, you can determine the optimum resource configuration for your pods at scale. You may find that as you add more CPU and memory, the app's ability to scale and service more requests scales linearly too, up to a point. And after that point, the performance may continue to improve, but adding more resources doesn't produce a proportional increase in application performance. And at some point, the incremental performance increases will either decrease significantly or disappear altogether, as the application is no longer able to take advantage of the additional resources you've assigned to it. And this may be because it can't make use of any more CPU threads, or it may be that it's experienced a bottleneck elsewhere in the system. Now, with the results from this testing data, you can decide on the optimum resource configuration for your pods. In my example, it could be here, where the performance increase is no longer proportional to the extra resources that are being added. Or it could be here, where we still see a performance increase, which is obviously useful, even though it's no longer directly proportional. And in some situations, you may have to make your choice based on other factors, such as the total number of pods running in the cluster, or the total number of pods running in a service, and how that may impact the endpoints object. Once you've determined the optimum resource configuration for your pods, you need to tell Kubernetes how much resource to give to your pods, using resource requests and limits. I'm sure you've all seen a pod configuration like this, which is telling Kubernetes that this pod must have a quarter of a CPU reserved for it, but that it can't use more than one CPU. Now, setting your requests low can be problematic. It's often done in order to increase the bin packing ratio of pods on worker nodes, as Kubernetes only needs to find a node with the minimum resource required to schedule a pod. So you can see how we're able to pack more nodes and more pods onto a worker node by setting our CPU requests low, compared to if we set it to something more realistic. But if too many of these pods get busy at the same time, there won't be enough resources for each of the pods to hit their CPU limits, and this will lead to contention and performance degradation in your application. Furthermore, configurations like this can introduce other issues when it comes to scaling, in particular with the horizontal pod autoscaler. Now, HPA constantly monitors the metrics for each pod that it's responsible for scaling, and it calculates a utilization value as a percentage of the equivalent resource request of the container in each pod. So this means that if you configure your pods with a low resource request, you will limit the full capabilities of that pod, because too many pods will be scheduled onto your worker nodes, which will lead to resource contention under heavy load. But also HPA scales off the resource requests and will aim to reach the target utilization that you configure. So if you set your HPA target utilization to 50%, which we often see customers doing in order to try and speed up the scaling process, it means that HPA will attempt to keep your pods at 50% utilization. And if you set your resource request to 1 CPU, even though you know your application can handle up to 8, then the HPA will artificially depress the pod's load to around half of 1 core, potentially wasting 7.5 cores of the resources allocated to it. So going back to our previous example for pod resources and thinking about the load test results from a few slides back, we can see that we'd be better off setting our CPU resource limit to 8. As we know, this is where the performance improvements slow down compared to the amount of resource being added. But we might also want to set the resource request to 8 so that we know the HPA is scaling off the correct resource or the correct metric, and also so we know that the pod won't ever contend for resources, further guaranteeing performance. Okay, so let's quickly summarize the key points that I've talked about today. First, you should ensure that you deploy your EKS cluster into a VPC and subnets that are large enough for your workload. If you need to, you can use the CNI configuration variables to tune the behavior of the CNI and the size of the warm pools to reduce IP address wastage. You should be aware of your AWS API limits and how they can impact both the functionality of your cluster as well as other workloads running in the same AWS account. You should choose the most appropriate blend of instance types and pricing models to optimize the cost of your workload. And you should optimize the configuration of your logging daemon to include or to reduce the number of API calls and hence reduce the load on the control plane. If necessary, you should switch out your logging daemon with something that's more efficient. And if you can, you should try and keep the number of pods per service to less than 250 to prevent the performance degradation associated with going past this number. You should make sure that you test your pods for scale individually as well as testing the application as a whole. And finally, you should ensure that you set your resource requests and limits appropriately to avoid issues with HPA and resource contention. Now, if you're planning on running a large-scale workload, please do get in touch. We'd love to help. This is a broad and deep topic, and I've barely scratched the surface in this short talk. There are many additional factors that I didn't have time to talk about today that could play a significant part in scaling your workload. And of course, the Kubernetes and the community is evolving all the time, creating new solutions to these difficult problems. So thank you very much for your time today. I hope you found this session useful, and I hope you have a great reInvent.